Hello everyone, welcome to my video on partial fractions. So this is a new integration technique that we're going to be looking at. So we've seen in previous videos use substitution, which involves compositions of functions. We saw integration by parts, which involves the multiplication of different types of functions. Now we're dealing with division. Whenever you have a division, we're using partial fractions. This is the first technique that should come to mind when we have a division of polynomial functions. So if we have integrals of the form nx divided by d of x. So nx is a polynomial. I'm using capital letter N for the numerator. So the value on top is called the numerator. The polynomial on top, numerator. And on the bottom we have capital D of x, which stands for the denominator. So whenever you have a division, we're using partial fraction. Partial fraction breaks up into two cases, and then from those two cases, it breaks up into four subcases. So we're going to look at all the cases involved. So the strategy that we're dealing with is we look at the exponents. So when I say look at the degree of the numerator, when I use the word degree, I'm talking about the highest exponent. So you look at the highest exponent of the numerator, and you look at the highest exponent on the denominator. If the degree of the numerator, so if the highest exponent of the numerator is bigger or equal to, so it's greater or equal to the highest degree of the denominator, then we use long division. Okay, so always begin partial fraction problems by looking at the degrees of the numerator and the denominator. So if the numerator is greater or equal to the denominator, we're going to start off with long division. If not, I'll show the subcategories in the event where the degree of the denominator is bigger. Okay, so let's go ahead and look at an example where we have to apply a long division. So in this example over here, we're not going to solve it, but let's just set it up. So we're given an integral of x cubed minus 4 divided by x squared plus 5x minus 6 dx. So it's a polynomial on the numerator and a polynomial on the denominator. So what we do is we look at the highest exponent. We look at the degree of the numerator. So the highest exponent on the top is 3. Okay. Whereas the highest exponent on the bottom, we have x squared plus 5x minus 6. The highest exponent is x squared. So notice that the degree of the numerator exceeds the degree of the denominator. This tells us to apply long division. So let's quickly do that, just as a quick recall. So long division, we set it up. This is the divisor. We're going to write it as x squared plus 5x minus 6. And then we're going to put x cubed minus 4 inside the root. I put them in decreasing order. So here if I have x cubed, what I add, you don't have to do it this way, but you could. Just to remind yourself, you have plus 0x squared plus 0x and then minus 4. Okay. So I reserve a space for the x squareds and the x. You don't have to write this, just remember that you cannot subtract terms that have different exponents. And now the game that we're playing is we ask ourselves, how many times we look at just the first term, the x squared, what do I have to multiply x squared to give me x cubed? Well, the answer to that is I have to multiply an x, because x times x squared is x cubed. So now what we do is we multiply the entire term here by the x that we have up here. So x times x squared is x cubed. I'm going to write it here. X times 5x is going to be 5x squared. I'm putting it underneath the x squareds. And then x times negative 6 is minus 6x. Okay, so I'm writing that in the x column. And now I subtract. When we subtract, I put it in brackets just to help us out. But you don't have to put brackets. We're doing x cubed minus x cubed. This we set it up so that we always get 0. If you don't get 0 here, you made a mistake. Okay. Next, we have 0x squared minus 5x squared. So be careful with the negatives. This is negative 5x squared. And then the next term is 0x minus negative 6. So we have two negatives now. Again, be careful, which turns it into positive 6x. Okay. And now we drop the negative 4. And now we play the same game again. What do I have to multiply x squared by to give me negative 5x squared? Well, the answer to that is just minus 5. Now multiplying the minus 5 by this entire bracket, we get minus 5x squared minus 25x, and then minus 5 times negative 6 is positive 30. And now we subtract. Subtracting over here, the negative 5x squared is cancelled to get a 0, as expected. if not we made a mistake. And now it's 6x minus negative 25, which is the same as 6x plus 25x, which gives us 31x. And then minus 4 minus positive 30 is negative 34. Okay, this is our remainder, r of x. Okay, so notice up here I wrote n of x divided by d of x, the numerator divided by the denominator, transforms into this piece over here. What is this? Well, q of x is the quotient, which is essentially what we have up here. This piece here, the answer, the solution, this is your quotient, this is your q of x. So whenever you're applying a long division, what you're going to do is take this division, the numerator divided by the denominator, and we're going to rewrite it in this form. So we're going to write the quotient q of x, which we got up here is x minus 5. So this turns into the integral of x minus 5, which this we know how to do. This is easy, just power rule for integration. And then it says plus the remainder, r of x. So let's write that here. R of x is the remainder, the polynomial we got in our remainder, which is over here, divided by the original denominator, d of x. So in this stage here, we're going to do plus the remainder, which was 31x minus 34, over the original denominator, which was x squared, what we have written over here, x squared plus 5x minus 6 dx. This we could integrate, this we could integrate, and now here we could continue by using partial fractions, and we're going to see this case in the next part of the video. Okay, so this is how you set up the integral whenever you have the case where the exponent of the numerator is larger than the exponent of the denominator. Now we're going to go ahead and see how to solve these types of problems. Okay, so we saw the strategy: if the degree of the numerator exceeds, is bigger than or equal to the degree of the denominator, then we use a long division. What do we do afterwards? How do we deal with the case when the degree of the denominator exceeds the degree of the numerator? This is the case that we want. That breaks up into 4 subcategories. Let's take a look at them. So if the degree of the denominator is greater than, specifically greater than, not equal to, strictly greater than the degree of the numerator, case 1, we have to look at the denominators. In the event that we have distinct denominators, we use the following partial fraction decomposition. This just means we're going to take the integral and we're going to break it up into pieces. But we have to analyze the denominator. So we have our numerator divided by the denominator. Evaluating the denominator, we're going to look at it, and if they're distinct roots, we're going to split it up in this form. The integral of a over a1x plus b1 plus b over a2x plus b2 plus all the way to z over anx plus bn, all that dx. Okay. But what do we mean by distinct denominators? Let's take a look at some examples. I just want to mention the example that we saw earlier when we used the long division. We broke it up into this integral over here, where I said the x is not a problem. We can integrate the x. We can integrate the negative 5. That's not a problem. But over here, notice that we transformed it. I just want to mention that we transformed this into a distinct denominator, because notice the exponent of the highest exponent of the numerator is a 1, and the highest exponent of the denominator is a 2. This is an example of this case, because the exponent of the highest exponent of the denominator is greater than the highest exponent of the numerator. Okay, and why is it distinct denominators? Well, just quickly, if we look at the bottom, we have two numbers that multiply to get to negative 6 and add to 5. Let's say, for instance, it was, just to make this easier, we could still do this. If we use product sum here, we could rewrite the denominator as x plus 6 times x minus 1. Rewriting x squared plus 5x minus 6 as x plus 6 times x minus 1. Now we have it as a distinct denominator. These denominators here are different. They're distinct from one another. X plus 6, x minus 1. So when we use the partial fraction decomposition, we're going to split this up into, let's say, in this example over here, this integral, let me squeeze it up here. If we focus just on this one, the 31x minus 34 over the x squared, which I'll rewrite as x plus 6 times x minus 1 dx. What this is telling us is that we're going to split it up into some number a, we don't know, a, over the first denominator, x plus 6, plus the second one, we're going to do b, some number b, which we're going to solve for later. You could take the integral of each term individually or put it under one big integral, it doesn't matter. Going individually is probably better. But now we're going to put some number b over the other denominator, the x minus 1. So we're splitting up the denominators. Okay. And now our goal is to figure out what a and b is. And let's look at an example to see how we do this. But this is an example of a partial fraction decomposition. We're taking this piece here and we're decomposing it into its distinct denominators, okay? So let's look at the next example. So in this example over here, we're still under case 1, distinct denominators. They give us the integral, and they ask us to evaluate this, the integral of 4 divided by x minus 4 times x plus 1 times x plus 3 dx. Typically, they give it to us in a form where it's not factored, so you might have to use your factoring techniques in order to put it into this form. Okay, so make sure you're comfortable with factoring. But in this case here, we're dealing with distinct denominators, distinct roots. So notice that x minus 4 is different from x plus 1, which is different from x plus 3. So we're going to use our partial fraction decomposition to split this up. So since we're in case 1, we're going to split this up into an integral of some number. Right now on top we have 4, but we don't know what the numerator is going to be. But we know it's going to be a constant. So we're going to have some constant a. That's what the partial fraction decomposition tells us. So it's going to be a over the first one, let's say x minus 4, plus the integral of some number on top, b, over... let's write it all under one integral. Not mandatory, but I think it's easier in the beginning. Over x plus 1, and then the next one is x plus 3. So plus c over x plus 3. So we're going to stop here at 3 terms. Okay. Now our job is to figure out these constants. What's the constant a, b, and c? What are those values? This way we could actually integrate these ones. Okay. So let's go ahead and do that. The way we do it is we ignore the integral signs. Okay, so focus on the integrand, what's on the inside. So on the left hand side, without the integral sign, we have 4 over x minus 4, x plus 1, x plus 3. Okay. And on the right hand side, what's in the integral is just a over x minus 4 plus b over x plus 1 plus c over x plus 3. And now what we do is we multiply both sides of the equation by this denominator over here. Okay. So we're going to multiply this on both sides. On the left-hand side, let me write it out. What we get is x minus 4, x plus 1, x plus 3. So on the right-hand side, on the left-hand side, the entire denominator is going to cancel, right? It's set up that way. We're just left with 4. On the right hand side, if we multiply this by x minus 4, x plus 1, x plus 3, we're going to distribute all this to each term individually. So if we focus with this on the first term, notice the x minus 4's cancel, but we're left with 8 times x plus 1 and x plus 3. Right? We're multiplying this entire thing times the first term, the x minus 4's cancel, leaving us with x plus 1, x plus 3 on top. We do the same thing with the second term. We get plus b. There's x plus 1 on the bottom, so it's going to cancel with the x plus 1, leaving us with x minus 4, x plus 3. And lastly, the third term, the x plus 3's cancel, leaving us with c times x minus 4, x plus 1. Okay. So we have to solve for a, b, and c. There's 2 methods of doing this. So let me show you method 1. Method 1 is my preferred method. If you could do it this way, I would suggest you do it, but in the beginning it's difficult. But we're going to cleverly choose x values to cancel out some of the terms. What do I mean by that? So at this stage here, we're going to let x equal negative 1. Okay. Where did I get negative 1? Well, I looked at my equation that I have here, and I asked myself, how do I want to cancel out my a? Well, I notice I have an x plus 1. So if I replace the x with a negative 1 here, the opposite number as what we're adding to, negative 1 plus 1 would give me 0, canceling out this whole term. And notice there's another x plus 1 here on my c. That's going to cancel out this value, because we'll have a 0 being multiplied by c times x minus 4. So this whole term is going to cancel. So if I let x equal -1, what I'm left with is on the left hand side of the equation 4 equals, this terms cancel because the -1 plus 1 gives me 0. So a times 0 times x plus 3 is 0. And we're left with b times -1 minus 4, -1 plus 3. And this we could solve for. So -1 minus 4, we get 4 equals b times -5. And -1 plus 3 is just 2. So this is -10 divided by -10, b equals -2/5. Okay. So we're able to solve for b. Now let's go solve for a. How do I solve a? Well, I could cancel out my b and my c term. How? They both have x minus 4s. So what am I gonna let my x equal to? Well, the answer to that is let x equal 4. Because 4 minus 4 is going to give me 0. 4 minus 4 is going to give me 0. So I'm going to replace my x with 4. So on the left hand side I have 4. And that's equal to a times 4 plus 1, which is 5. And 4 plus 3, which is 7. This one cancels, this one cancels. So I could just solve for my a now. Divided by 35, I get a equals 4 on 35. Okay. And then lastly, I do the same thing. I want to find my c. At this point, you could plug in any value you want, but the easiest value to choose is x equals -3, because at -3, it's going to cancel out this term, and -3 is going to cancel out this term, and we can solve for our c. So let x equal -3. So the left-hand side of the equation is 4. This cancels. We're left with c times -3 minus 4, which is -7, and -3 plus 1 is -2. This implies -7 times -2 is positive 14. So this is c equals 2 on 7. Divide by 14 on both sides, we get 4 on 14. Divide by 2, 2 on 7. So now we found the parameters a, b, and c. Now, this is all side work. We found the values of the numerators here. So now we could go back to all this and plug them in. And it's going to allow us to solve the integral. This we don't know how to integrate, but now if we break it up into the partial fraction decomposition and deal with it by parts, well, now we're able to integrate these terms. So this is all side work. Coming back to the integral, we now know this is equal to the integral. A we said was 4 on 35. All that on x minus 4. Plus the integral b we said was -2 on 5 over x plus 1 dx. And c is 2 on 7. So I'm just taking the integral of each term individually. Take this out. And now how do we integrate these terms here? Well, this isn't too bad. If we ignore the constants, so let's continue in block. I'm going to pull out the constant, the 4 on 35. And I'm left with 1 over x minus 4 dx. For the first term. For the second term, I'm going to pull out the -2/5. And I'm left with the integral of 1 over x plus 1 dx. And lastly, we take out the 2/7, and we're left with the integral of 1 over x plus 3 dx. Okay. How do we deal with the integral of 1 over x minus 4? Well, this may look complicated, but this shows up often. It's essentially just a u substitution. In each case you're doing a u substitution, you're letting u equal the denominator. So if I focus on the first one, and we do a u substitution, we let u equal x minus 4. Well, the derivative is dx. So what you're left with is just 4 on 35, integral of 1 over u, and dx is being replaced with u. And we know the integral of 1 over u. The integral of 1 over u is just ln of u. So let me just write that. ln of u. But wait, what's u equal to? U is equal, come back in terms of x minus 4. And this piece is done. And we do the same thing with the other ones. It's essentially just a u substitution. So we get -2/5. If we do the same idea, u substitution over here, we get ln of x plus 1. It's essentially just another u substitution, like u equal x plus 1, you get 1 over u, take the derivative, take the antiderivative, the integral, 1 over u, it's ln, and it's ln of whatever your u was, which is essentially just in this case the denominator. So it's the exact same thing, and once more you're doing the exact same thing. So work out the details if you don't believe me, and do the u substitution on each case, you'll get the same answer as me. So this turns out to be ln of x plus 3. And since it's an indefinite integral, we have plus c. And this is the final answer. Okay. So this was a case 1 with a partial decomposition with distinct roots. All the denominators here were different. Okay. Let's go ahead and look at our case 2. So case 2 of our strategy is repeated denominators. How do we break up our partial fraction when we have repeated denominators? So the partial fraction decomposition, so the way we break it up, we have our numerator divided by our denominator. Our denominator has repeated roots. We're going to separate it as the integral of a, our constant on top, divided by a1x plus b1, plus another constant b, divided by, here what's different is that we have a1x plus b1, all that squared, plus dot dot dot, all the way to whatever constant we have, divided by a1x plus b1, the same term, but to the exponent n dx. So we split it up depending on the exponent of the denominator. Let's go ahead and find the partial fraction decomposition. We won't solve it, but look at this example. How do we split this up? So the example that we have here is 6x plus 13 divided by x cubed times x plus 1 squared dx. And how are we going to break it up? So first of all, we have to catch that it's repeated. Why? The exponents of the x is cubed. So think of it as x times x times x. And x plus 1 is squared, so it's x plus 1 times x plus 1, so it's repeated. So what we have to do is deal with each term individually. So we have to deal with, what this is telling us is to break it up into 1 over x. But since the exponent is cubed, we have to do each exponent. So 1 over x, oh sorry, not 1. We don't know what the numerator is going to be, we have to call it a. Let's put it all under one integral. So the next one is going to be b over, on the exponent, it's cubed, so we have to go through each stage. So we did 1 over here. Here we have to do 2, and then we have to go get 3. Okay, so that's what this is telling us. Depending on the exponent, you have to go get each term. Okay, so that was for the x. We still have the x plus 1 squared to deal with. So that's going to be plus d over the first exponent. So it's x plus 1 squared, so we have to do x plus 1 on its own. And then plus e, we have to deal with x plus 1 squared dx. If this was cubed, we would have another term, f over x plus 1 cubed. If it was to the 4, you would have another one, g over x plus 1 to the 4. So you have to do all the exponents, okay, each degree, up until you get to 3 or 2 or whatever the value is. Okay, that's what the decomposition is for the repeated case. Okay, so very similar to the first case. Let's go ahead and take a look at an example and actually solve it. So here we have to evaluate the integral 5 over x times x plus 1 all that squared dx. Let's go ahead and first of all notice that the degree of the denominator is higher than the degree of the numerator, because here we have x plus 1 squared, which would give us an x squared, times the x over here would give us an x cubed. So the highest exponent of the denominator is x cubed, and that's bigger than the highest exponent of the numerator, which in this case would be x to the 0. So we don't have to apply long division. That's always one of the first things you should look out for. So in this case, there's no long division. The next thing you have to do is identify the denominator. So in this case here, if there was no squared here, this would just be a distinct root case, or case 1, because we had x and x plus 1. Since we have the squared here, it now becomes a distinct case because we have x and x plus 1 with a repeated denominator because we have the exponent 2. So how do we break this up? So using the partial fraction decomposition, this is going to break up into a over x plus, now we deal with the x plus 1, b over x plus 1, plus, and now c, because we have to deal with the x plus 1 squared. We go get all the exponents. So now we know it's going to separate into this, a, b, and c. Okay, now we have to actually solve for those values, a, b, and c. How do we do that? So again, same as we did in the first one, we focus on just the integrand of both cases. So we look at 5 over x times x plus 1 squared, and we set that equal to whatever's in here, a over x plus b over x plus 1 plus c over x plus 1 squared. And we solve it in the same manner. We multiply both sides of the equations by the denominator. So if we multiply by x times x plus 1 squared, notice that here this is going to cancel with this, leaving us with just 5 on the left hand side. And on the right hand side, we're going to distribute this to each term. So we have x times x plus 1 squared times a over x. The x's are going to cancel, leaving us with a times x plus 1 squared. X times x plus 1 squared times b, well, there's an x plus 1 here. We have b times x times 1 of the x plus 1s, because x plus 1 cancels with one of them since we have a square. And then lastly, c, x times x plus 1 squared. The x plus 1 squares cancel, leaving us with c times x. Okay. So now I'm going to show you how to solve this using method 2. So you could use the method that you prefer. I showed you method 1 already, where you choose x values to cancel out terms. In this case, it would work as well. You could let x equal 0. That would cancel out the b and the c term. You could solve for a, so on and so forth. Let me show you the second method. So method 2. So you use the method that you prefer. In this case here, method 2, it involves creating equations. So what you're going to do is, and sometimes method 1 might not work and method 2 will work, and sometimes method 2 won't work and method 1 will work. It really depends on the problem, so you should be comfortable with both methods. Don't specifically choose one, because that method might not work depending on the problem. So for method 2 specifically, what you have to do is expand. So at this stage here, I'm going to expand the x plus 1 squared, so that's going to give us a times x squared plus 2x plus 1. The bx I'm going to distribute, giving me bx squared plus bx plus cx. And the a I'm just going to distribute it in, so it's ax squared plus 2ax plus a. Okay. And now what you do is you create an equation with each degree. What do I mean by that? So we're going to look at the x squareds. The highest exponent that we have is an x squared in here. We're going to create an equation with the x squareds. We're going to create an equation with the x's, and then we're going to create an equation with the constants. Okay. So what do I do? All the terms that have an x squared, let me underline them. There's ax squared, there's bx squared, and that's it. On the left hand side, we could think of this as 0x squared. Let me just write it for it to be clear. We could think of it as 0x squared plus 0x plus 5, right? It's not really useful, but just remember we have a 0 on the left hand side. So to create an equation in terms of the x squared, we have a 0 on the left hand side of the equal sign, and that's equal to, do not keep the x squared, just take the coefficients in front. So 0 is equal to, in this case we have a, and here we have the b that's sitting in front, so a plus b. This is one equation. So the relationship between a and b, if I bring the b over, this means that a is equal to negative b. Okay, that's helpful. So we got that from the x squared equation. Now let's look at the x's, all the terms that have an x. So over here, I'm just going to do like a squiggly line. We have a 0 on the left hand side. We have the 2ax here. We have a bx and we have a cx. So we get the equation that 0 equals, because on the left hand side we have a 0 here, we have equals 2a plus b plus c. Okay, so don't include the x's, but this one's complicated because we still have 3 unknowns, so that doesn't help. Let's go look at our constant. Based off the constant, let me circle it. On the left hand side we have a 5, we have an a here, and that's it. So we get the equation 5 equals a. That gave us one of our numbers. We know 5 is equal to a. And since we know a is equal to 5, well, now we know a is equal to negative b. This implies that b is equal to negative a, right? If I divide both sides by negative 1, we get b equals negative a. And a we know is 5, so b is equal to negative 5. And we're done. We found a and b, and now we could go ahead and solve for c using the equation that we have in terms of the x's. So we have 0 equals 2 times a. A we know is 5, so 2 times 5, plus b, which now we know is negative 5 up here. And now c is what we're looking for, plus c. This gives me 0 equals 10 minus 5 plus c. 10 minus 5 is 5, and I bring it over, it becomes negative 5. So c equals negative 5. So we found all three of our constants. Okay. So now that we found our constants, we go back. So this is using method 2, where you create the equations based off the degree of, let's say, each term of the polynomial. Okay. So method 1 and 2, make sure you're comfortable with both. Now that we found our coefficients, let's go back to the integrating part. So this is all side work. We could write the integral now as the integral of a, which we said was 5, so 5 over x, plus b, which is negative 5, so let's put a minus 5 over x plus 1, and c, which we said was negative 5, minus 5 over x plus 1 squared dx. Okay. And now we could integrate each term. Okay. So the first one's easy. If we pull out the 5, we're left with the integral of 1 over x, which we know. That's easy. This one over here, if we pull out a minus 5, we're left with the integral of 1 over x plus 1, which is also easy. We saw this in the previous example. And then here we have negative 5, which I'll pull out, and we're left with the integral of 1 over x plus 1 squared. Okay. Still pretty easy, requires a bit of work, but essentially, this one over here, we're left with 5 ln of x, because the integral of 1 over x is ln of x. Here we're left with minus 5. We get this with a u substitution, so we let u equal x plus 1. The derivative du is equal to dx. Substituting, you get 1 over x, giving us the integral of 1 over x, which we just saw is ln, but in this case it's ln of u. I'm skipping steps here, but u is essentially just x plus 1. And that's it. So work out the details. It's essentially a u substitution with u equals x plus 1, and you'll get it. Okay. And then lastly, we have this one over here, which again, you'll get it with a u substitution, letting u equal x plus 1. If we let u equal x plus 1, this one I'll work out. We have minus 5 integral 1 over u squared. And du equals dx. So this is just du. So we're integrating 1 over u squared. Let me just put this on the side. U equals x plus 1. And 1 over u squared is the same as u to the negative 2, which we just applied power rule. So this gives us 5 ln of x minus 5 ln of x plus 1 minus 5. Add 1 to the exponent, divide by it, you get u to the negative 1 over negative 1. So here the negatives cancel, turning it positive. 2 negatives make it positive. And u to the negative 1, well, u we know is x plus 1. So we could just drop the exponent. U to the negative 1 is the same as 1 over u, giving us 1 over u, which is x plus 1. And since it's indefinite, we have our plus c. Okay, so you can write it as 5 over x plus 1, but this is fine. Or you could factor out a 5 in each case, that's fine as well. So this is the final answer. This is partial fraction case 2, where we have repeated denominators. Hope this helped. I hope you have a better understanding of case 1 and 2 for partial fractions. The first thing you should always analyze is the degree of the numerator. See if it exceeds the degree of the denominator or equal to the degree of the denominator. If that's the case, you have to do a long division. If not, you break it up into 4 cases. So we saw the first 2 cases. I'll show you the third and fourth case in another video. So keep practicing. I hope this helped, and I'll see you in the next one.